In the lecture series on tensors, we are at the lecture number 1, and today we are going to talk about what is a tensor. In order to understand the concept of a tensor, we need to understand the concept of a components. As you know that any physical quantity may depend upon the directions. So in order to determine the components or the dependence of a physical quantity on direction, we can use a Cartesian or rectangular coordinate system. And this coordinate system is made from the line along horizontal, which is called x-axis, a line along a vertical axis, which is called y-axis, and a third direction, which is perpendicular to both of them, is called z-axis. And the point where they all meet is called origin. Now we can use this Cartesian or rectangular coordinate system to determine the components of any physical quantity. So let's do that, and first let us consider scalar quantity. You know that a scalar quantity is a quantity which has only magnitude and a proper unit and does not need any direction. So it does not depend upon the direction, which means that the scalar quantity has only one component, or in other words, it is independent of any of the three physical dimensions. For example, if we talk about the mass of certain object, which is equal to 5 kg, so we don't say that it is 5 kg along x-axis or y-axis or z-axis. It has no effect along any of these directions, so it has only one component, which is given by the number of the magnitude of that mass or that physical scalar quantity. Similarly, another scalar quantity is a temperature, and again only the magnitude is considered as a component, and it has no dependence upon the three directions we are talking about. But there are other physical quantities which can depend upon the directions. For example, a vector quantity, and in this case here you see that in that the components of a vector depend upon physical dimensions. For example, in this case you see that in two dimensions we have x-axis horizontal and y-axis the vertical axis, and this vector quantity which is called A has an effect along x-axis, which is called AX, and has an effect along y-axis, which is called AY. So in two dimensions this vector has two components, that is AX and AY. And if we increase the number of dimensions, for example 3 dimensions, as you can see over here, then the components of vector can also increase, and in 3 dimensions you see that we have 3 components of this same vector A. So the effect of this vector A along x-axis, effect of a vector A along y-axis, and effect of a vector A along z-axis. So it means that vector is that physical quantity which has effect along all 3 directions, and these effects are called components of a vector. There are numerous examples of such quantities, for example force, velocity, torque, acceleration, and so on. So all these are vector quantities, and they depend upon the directions. Now over here a very important question arises, and that question is that whether we can have a physical quantity which has more than 3 components in 3 physical dimensions. And the answer is yes. So we can have a physical quantity which has more than 3 components in 3 dimensions. So let's understand this with the help of an example. An example is very well known. It is a stress which has 9 components in 3 dimensions. Let's see how it is possible that stress has 9 components in 3 dimensions. You know that stress is defined as force per unit area, and now we want to see that how stress can have 9 components. For this we consider a beam. This is a beam of, for example, concrete, and in this beam we take a certain point, and then we draw our Cartesian coordinate system. Let's say this is a horizontal x-axis, and this is a vertical y-axis, and third dimension z-axis. And now with the help of this three-dimensional Cartesian coordinate system, we would like to make measurements of a stress on this particular point. So to do this, we need to draw an imaginary area. As you can see over here, it is a three-dimensional area. Now since area is a vector quantity and it has also three components, so force is also a vector quantity which has three components, and area is a vector quantity whose direction can be determined with the help of right hand rule. So if you take this area which is parallel to the y-axis and its direction is along x-axis, then we need to have apply on this area force, and then force will have three components on this area. For example, fxx is a force along x-axis on this ax, and fxy is a force along y-axis, and fxz is a force along z-axis. So you see that only the one component of the area along this plane, there are three components of a force. And similarly, we can have on the other these areas three components of a force and three components of force here. So if you count, then we have in total 9 components of force and area together. That's why sigma, this stress, has 9 components in three, although there are 3 dimensions, but its components are 9. In order to see that how these force can generate 3 components with 1 component of area, let's go into detail and see the force along x component of the area. So force along the x component of area in this beam example will be, we will select this imaginary cut over here, and this imaginary plane actually has an area ax because it is the x component of the area, and then the force on it is 3-dimensional, 3 components. Force has a vector quantity, so it has a 3 dimension. So if we calculate the stress with these 3 components of a force on this area ax, so we will get fxx by ax, let's call it sigma xx, and then we will have fxy over ax, let's call it tau xy, and then there will be a third stress component that will be fxz over ax. So you have seen that for the one component of a area, we have 3 components of a force, of a stress, because of the 3 components of a force. And similarly, if we take the imaginary cut along the parallel to the x-axis, and its direction will be along y-axis, that's why its area is called ay. And if we calculate all these 3 components because of the force on this area, what we will get is tau yx and sigma xy and sigma and tau xz, and the same components we call it by x by sigma. And if we take the third cut or third imaginary area, that is perpendicular to the z-axis, so this will be az, and if we calculate again the components, then we will get tau zx, tau xy and sigma zz. So with this you have seen now that the stress is a physical quantity which has actually 9 components, that is, you can see over here in this matrix. So now the problem arises, what we should call, what name we should give to this physical quantity, and the option was to call it a tensor. So if we call it a tensor, that is something which has more components, that is 9 components in 3 dimensions. So we also have to rename our previously defined quantities. For example, we had a scalar, if you remember, it has only 1 component, and we call it that it is a rank 0 tensor. So we also call it a tensor and give it a name, a tensor of rank 0. On the other hand, if you remember, vector had 3 components, and we call it is a rank 1 tensor because it had 3 components in 3 dimensions. But now the stress is having a 9 components, so we call it a tensor of rank 2, and it has a rank 2. So it has no specific name, but we call it a tensor of rank 2. So in this way you see that tensor is nothing but a physical quantity which has certain components along directions. So scalar is a tensor which has only one component, vector is a tensor which has three components in three dimensions, and a tensor of rank 2 like stress has 9 components in 3 dimensions. So tensor is a general name given to a physical quantity depending upon its components in different directions. Since scalar and vectors are well established names, so these are not replaced with tensor of rank 0 and tensor of rank 1 commonly, but since tensor of rank 2 has not given any specific name, so we use it as a tensor of rank 2. So in this way we have now understood that tensor is nothing but a physical quantity which has varying dimensions, varying components in different dimensions, and therefore it can be a tensor of rank 1, 2 or 3, but tensor of rank 1 is called scalar, tensor of rank 2 is called vector, and tensor of rank 0 is called scalar, tensor of rank 1 is called vector, and tensor of rank 2 is called tensor of rank 2. It has no specific name. I hope this was helpful to you. Thank you very much.